Yeah, I stopped this, then I'm starting again. So I'll have two parts, but eventually we'll merge everything. Come in, I'm trying to connect to my iPad. No, my phone will soon die. Okay, let's continue. So, where are we? Yeah, we're here. Now we do. Okay, I don't know. I think I should do this now. There's something called linear interpolate and evaluate. Right now we're doing it separately, right? We'll interpolate first, then get a polynomial, then we'll evaluate that polynomial to get the value. You could technically do it at once. Okay? So let's, yeah, even in code. So let's get a formula that can do it at once, so that we don't have to do it all the time, right? So it's always like we have two y values, right? Making sense? We usually have two y values. So this is like y1 is connected to y2, right? That's how all our pairs have been now, right? Then this is usually like y1 times L0 of x, right? Plus y2 times L1 of x. So I'm making it generic so that we can simplify down. So y1 times, what is now L0 of x? 1 minus. So let's call it r. It's actually, let's just call it r rather than x. Okay, r is the let's say like when we're partially evaluating at c equals 3, r will be 3 in that case. Okay, so that will be 1 minus r plus y2 times r. Cool? So this is y1 minus y1r plus y2 times r. Right? You can collect r. So this is y1, let's say plus r, y2 minus y1. So this is an example. This is like, with this method, you can interpolate and evaluate at the same time. Does that make sense? So we'll now do an example. So R is representing the point you want to evaluate at. Let's do an example. Okay? So let's say, like this one that we have so far. You know, we wanted to say c equals 3, right? And I've gotten all the c lines. So let me use this one because this one is more interesting, right? 2, 5. So if we wanted to do this, we'll have done 2 times what? L0 plus 5 times what? L1, right? Which is 2 times 1 minus c, right? Plus 5c, right? Which is 2 minus 2c plus 5c, which is 2 minus plus 3c. So now I've done the interpolation. Now we do the evaluation, which is c equals 3, right? So that will be 2 plus 3 times 3. C equals 3. Which is what? 2 plus 9, which is equal to 11. Now let's use this other one, right? y1 is what? 2. y2 is 5. And r is 3. So we just do it here. 2 plus 3 times 5 minus 3. Minus 2, sorry. So that's 2 plus 3 times 3, which is 2 plus 9. So fast. Do you get it? Okay. interpolate and evaluate at once. I'll do it again. It's way faster, like way faster. And there are two ways to do it, right? So I think the initial way we learned was this. But then if you see this has two multiplications, right? It has like y1 times r and y2 times r. It's the same thing. Y1 times r and y2 times r. In fields, in prime fields or finite fields, multiplication is more expensive than addition. So this one is doing two multiplications. That's like here and here. And then it's doing three additions. So three additions and two multiplications. But then this other one, which is exactly the same thing, but just written in a different way, is doing two additions and one multiplication. So it's way faster. You get? So just using this one instead of this one might mean that your code runs twice faster. But it's exactly the same formula. Okay, so I'm going to do it again.
Why do you have like the second line? Why do you have 1 minus r and r?
This is like check 0.
Can you just represent it directly? Instead of like L of x.
So L of r.
Yeah. The other place to see directly from
Oh, you want C?
No, where you
Okay, I get what you mean. So, is your question answered?
Sorry, please explain 0, but at r point,
So if you look at Lagrange, this thing, it's always like the output, that's the y value, which is a constant. So there's no variable there, times the Lagrange basis with the variables. So it's usually the Lagrange basis that has the variable that you want to evaluate at. So we're always evaluating at something, maybe r or c or whatever. So that's why the Lagrange basis is taking that r. Does that make sense? Oh. So if you look at this is what? y1 minus y1 times r plus y2 times r. We have how many multiplications here? 2. How many additions? No, not 3 then. Right? I thought it was 3. Then the other one is like y1 plus r times y2 minus y1, right? So there's a multiplication here, which is just 1. That's the only place for multiplying. But then we have an addition here and an addition here. So that's 2. Addition and subtraction are the same thing in terms of like time. Does it make sense?
So the r is the c value.
The r is the c value, yes, or any value that we're evaluating. We're always partially evaluating something, right? Does it make sense?
Yes.
Should I go over this thing again? Or
I think the only difference is that for this one, you are putting the values at the beginning.
yes.
This one, you are putting something and at the end, you now putting the values.
Yes.
They're very different.
Yeah, exactly the same thing. It's just that it's faster. Like once you have simplified it down, your code can just like use this
Just looking for the rest
directly.
of those values instead of the
Yes. Just evaluate the r.
yeah.
So which one is more expensive?
The top one is more expensive. Then faster.
So you just give us
Which one do you see the
the cheapest one at once, because we've gone down from more expensive to this one, and now we've seen another.
You need to see the
flow.
you need to see the range, yeah. Because of it's not done. It's not done. Like the field is not done. More things are going to come out. If you are not in the habit of seeing how one thing is, then how it got better, you need to be in that habit. Does that make sense? So should I still do this again? I should still do it again.
No, it's not that.
Okay. And I'll do it again. I'm writing it again. So usually when we have 2 points, right, we do 2 times L0 of x, right, plus 5 times L1 of x. Then we solve, and we get some polynomial, right? So let's say 2 times 1 minus x, or let's say, okay, let's say c, right? Plus 5c, right? So that's 2 minus 2c plus 5c, which is equal to 2 plus 3c. Then you now evaluate it with your concrete c, right? So you have like a c value. Let's say c is equal to 3. You now evaluate it. So we're trying to stop breaking it into like 2 steps and just do everything at once. Does that make sense? So the way I did that was by assuming, regardless of the value of y1, I don't care whether it's 2 or 3, I want to know what the structure is for just like any value, y1. So I can replace it with any value. So y1 times L0 of what? Of r, plus y2 times L1 of r, right? So that's y1 times what? 1 minus r, plus y2 times r. So that's y1 minus y1r plus y2r. Then I can factor out, to prevent doing more multiplication than I need, I'll factor out r. So that's y1 plus r into y2 minus y1. So now this does all of this, but at once. Does that make sense? Are we good? Are we good? Doesn't have to be perfectly clear, but just take it, and then if questions are coming, just. So let's just finish this. Even me, I'm tired. I am tired too. So let's continue. So this is y1 and this is y2, right? y1, y2, right?
Yeah.
So we need to solve all of them. And r is what? Does this make sense? Like we're partially evaluating at 3. So what we do now is we just use this formula. So that's what? For the first one, 0, 0. That'll be what? 0 plus 3 times 0 minus 0. I'm just showing it. 0, right? Then 0, 3. That'll be what? 0 plus 3 times 3 minus. Is this making sense?
No.
C is 3. C is 3, which is our R. Right? So we're doing what? Y1. What is Y1? What is R? What is Y2? What is Y1? Does this make sense? So this is 3 times 3, which is what? 9. Make sense?
Yes.
Then we have 0 to 0 again, which is the same thing as the first one. So I'm not even going to do that, right? That's just 0. Make sense?
Yeah.
Then we now have what? 2, 5. What is Y1? What is R? What is Y2? What is Y1? So this is what? 2 plus 3 times what? 3 times what?
3 times 3.
That's 9 plus 2, that's what?
11.
So this means that our new array is basically like it's so fast. But now let me show you how. So now, yeah, how do you arrange it exactly? So the arrangement usually just follows from if you take your pairing in a certain way to just like, as you're just doing it, just adding it into. So there's a way to do it. But if that's not clear, you can see that this position is actually 0, 0, 0, 1, 1, 0, 1, 1, right? And if you look at the things that are constant, in this first one is what?
0, 0.
And the next one is what?
0, 1.
The next one is.
1, 0.
So that's why the result just goes like sequentially. But if it was shuffled for some reason, then you need to just like shuffle it in the correct spot.
That's how I used to.
Yeah, that way you see. Oh, so that it will be sequential. If we had used B now, it would have been might be the same thing actually. It will be the same thing. It will also be sequential. Funny enough. Yeah, A2 it will be the same thing.
So when do we now expect it to not be sequential?
It will almost never be non-sequential. The reason why is because we're taking our pairing index from the top down.
Okay.
Imagine if you had took your pairing index from the bottom up, right? Then you now have had like 1, 1 first, right? Then, but you just put it at the last position. Does it make sense?
Yeah. 4 points.
Yeah, we're having 4 points.
Like
From a cube to a square.
I can still like
Do it again. Yes, to like a line. And you can do it again to a point.
And then from the point do it again.
There's nothing again. So you know it was C that we partially evaluated. So C is changing, right? So if you look at this top one, C changes 0, 1. But the things that don't change, A, B, right? So that's 0, 0. So that means that the value that we get for this should be put in the 0, 0 position of the array. And likewise for the rest. So this one is 0, 1, which will be here. This one is 1, 0, which will be here. And this one is 1, 1, which will be here. Does it make sense? So does 3 make sense? Yeah. Okay, let's do A. So I'll pair it up. Yeah, let's pair.
So you just check for the B and C parts.
I'm coming. You're saying that we want to partially evaluate A, right? So we're partially evaluating A. That means we're looking for where A is different. But B is the same. B and C are the same. So that's what? 0, 0 will be paired with what? 1, 0, 0, right? Right?
Yeah.
Only A changes.
Yeah.
So you mark this and you mark this. So now it's picking first. You know the other one was picking first, second. It was picking them side by side. This one now is picking this and it's picking this. So what's the next one? 0, 0, 1, right? 1, 0, 1. So it's picking here and it's picking here. There's a pattern. You guys need to understand this pattern when you're implementing. There's one way to do it. There's another way to do it without the pattern, though. The way without the pattern is actually faster. Funny enough. But yeah, 0, 1, 0 is what? And then what? 0, 1, 1 is what? Right? Now let's imagine we now solved it. Where are we going to put it? So A is the one that is changing, right? So we're looking at just BC. That's 0, 0, 0, 1, 1, 0, 1, 1. Still sequential. And that will be the same thing for B. It's always like that as long as you take it from the top. Yeah. I don't know. I can't remember. But regardless of what, it doesn't matter. You don't need it to be ordered. Just look at your condition and then just.
Let's continue from that 0900.
I think from that 09000.
That's already the other one.
Other one.
The other one. So you just do it down to.
So now this is a polynomial of just like AB. This was ABC, but you have removed C. So now this is just AB. Does it make sense?
Yeah.
So meaning that if we take this down to a point, no, if we take this down
If it-
to a line,
Yeah.
then from a line
To a point. Yeah.
that's all.
That's full evaluation.
That's the complete evaluation.
That's evaluation. That's when you have said A is equal to something, B is equal to something, and C is equal to something.
We don't need to do B or C to. We don't need to do for B and A to prove anything. We have just
Damn, so you have fully evaluated it. So you have gotten, when you have f of a comma b comma c, and you set values for a, b, c,
Yeah.
you're going to get a single value out. That's that point you're talking about. But if you have just partially evaluate, you're going to get something of a lower dimension.
In summary, instead of the computer to do the work and to be slow, we are now doing the work so that it will be fast.
Which one?
The point is that I prefer normal evaluation that we know before.
No.
So
Eh,
that one is
This is also evaluation,
Yeah.
but it's not like, rather than representing it in coefficient form, we're representing it in evaluation form. The reason for this is that, remember the Fibonacci case?
Yeah.
The trace is already the evaluation of some polynomial. So normally you're not supposed to like interpolate first, right?
Okay.
Then do whatever you want to do.
Oh.
But now with this, you don't need to waste that space or time interpolating.
Then,
You can do stuff with this directly.
we are interpolating
Yeah.
and evaluating.
You're not you mean, what do you mean?
Like this part that you were saying, you have used that formula there.
Yeah, the y something, right? Yeah, you're still doing some interpolations, but they're like very small because they're lines, right?
Yeah.
So it's like really fast. And it's not even interpolation anymore. See, it's just like 2 multiplication and 1. Yeah. It's like two multiplication and 1 addition. No, 2 additions and 1 multiplication. Like it's so cheap. That's how cheap the line stuff is. But then we are doing for anything bigger, then you're not doing that numerator, denominator, then you evaluate.
So if you and Francis did not find this one, we would have written that long thing.
If we didn't find it, we could have just told you this directly.
Oh.
So
Okay, it's possible that there's a better one than this.
I don't know. Maybe.
Thank you for
No,
finding it.
it's not that you find it, that there's really research that we're saying because I'm just gonna hear this.
Huh? What do you say?
This one was
Yeah.
it was implemented in this one.
Yeah. So we saw someone implementing with like evaluation form, and we saw that this is how they did their partial eval. But we didn't know like where did this come from? Yeah. And there's no way you can know that this is like, unless you know that the Boolean hypercube is made up of lines. There's no way you will link it to like, oh, they are lines, and then all this kind of thing. So yeah, exactly. Does it make sense? Yes, evaluation form. But then we're doing partial evaluation under evaluation form. Yeah. I'm done. No. I'm done. No. So we're good, right? Any questions? Alright. So tomorrow you guys should just relax a bit first. Then try and understand it again. Then tomorrow we'll do a design, like code now. We'll do a design session. And if you guys have any questions, you can just let us know by tomorrow.
Can you give us like polynomials of points that you can just
Evaluate.
evaluate?
I'll send it on Telegram. I'll send it on Telegram. If you want to do it, you do it. If you don't want to do it, don't do it. But it's just practice to solidify the theory.
So you put the answers there too.
No, I won't put the answers now.
No, like the final answer that you're expecting.
I won't put anything. Don't worry, tomorrow.
Tomorrow, come and